We present compact Gaussian hair, termed CGHair, a novel hierarchical clustering and encoding framework for compact human hair modeling. Given monocular video frames, we first reconstruct hair strands with our efficient strand generator. The strands are grouped by hair cards, which are further clustered into card groups. Each card group is assigned to a shared Gaussian texture for compact appearance modeling. A specialized global MLP is used to compute spherical harmonics, SH, from the Gaussian textures. The 3D Gaussian Splatting rendering is then adopted to perform free view rendering. Here we introduce our efficient image-based strands generation pipeline. We use perm decoders to generate a guide map and a style map from guide code and style code. The resulting maps are concatenated into a geometric hair texture and then decoded into 3D strands by a PCA decoder. We then attach cylindrical Gaussian primitives to the strands and optimize them from images using the 3DGS. We cluster the hair strands and use a guide strand to represent each cluster. We then calculate a local frame for each segment of the guide strand. The hair card mesh geometry is then constructed following the strand, with a card width to ensure all strands fit within the card. With the card and strand, we then generate the hair card geometry texture. The strand's points are projected onto the hair card, then represented by the barycentric coordinates and a delta offset along the mesh surface, normal. On the UV plane, the projected points are connected and fitted by a 2D spline curve to form a 2D strand texture. For our compact hair representation, we further group hair cards into clusters using the generated geometry textures. A logit is assigned to each strand and then processed by a Gumbel softmax operation to generate a soft index. The index is then used to fetch a strand appearance feature from a Gaussian appearance texture, which is shared by all the cards in the cluster. Then, a lightweight globally shared MLP decoder is then used to decode the feature into SH coefficients for rendering. In this way, it achieves over 270-fold per meter compression. Here, we present the results of CGHair, including reconstructed hair strand geometry, Gaussian hair rendering, and dynamic simulation.